Okay, and we're recording. Go. Okay, give people like a minute to check in.
Yeah,
Pretty sure you can make this disappear, right? Hide video. Oh.
yeah.
There we go.
I think I created other videos of showing a different person's name, but I also hit the mission control, so it's still. Maybe can you just minimize that bar?
Wait, is it on
Yeah.
screenshot like multiple people are able to?
Yeah.
Okay. Share the screen.
Yeah. Yeah, you need to join the data science public where you can do the assignment. So on campus groups, you need to join. Start in 1 minute.
So we're gonna start in 1 minute, guys. Let's say it again. Hey everyone, we're gonna start in like 1 minute. All right. By now, I hope you guys signed in. Of course, this is the sign in QR code. So if you haven't scanned it, please do. And so, yeah, today's March 2nd, and we are doing yet another meeting. Okay, yeah. All right, so yeah, we're doing another meeting today. Today's March 2nd, and some updates. So,
Update on data because we actually got a hold of Ernest, the main guy, which this meeting probably should have happened a month ago, but we got it yesterday, so we're kind of so some updates. Some of you were wondering about like the sponsoring company. It is purposely blinded from us until like right before or even when the event starts. They don't want you to look at the company and figure out what data they're going to give us. So it's intention that you won't know that the company is providing the data until the day of. But historically, it's been companies all over the place. So like, let's see, so what data have you seen? Like,
yeah, so Expedia, which is like the traveling company. The Canadian Women's Rugby League was one. DataFest and Indeed.com, like the job search. That was another one. And last year
was from universities like Cambridge Psychology or something like that. They gave us a psychology. Last year, the main problem was actually how to clean the data. They were a bunch of psychologists who didn't know how to write down data like in a usable format. So they spent all this time basically just like managing this data into like real like features and like that. Yeah, so we have all the logistics kind of handled. They're getting us 4 rooms. So one of the rooms, we're gonna have a main auditorium room, much like this. It's going to be for the hackathon. We're going to have another room for speakers. We're going to have another room for posters and another room for mentoring. So if you want to do the hackathon and need help, there's going to be a room just to get help room. And if you want to take a break and go see some speakers, go see some speakers, or even go see some posters. By the way, we're still obviously now that we have 4 weeks left, and we finally got confirmed that we have 4 rooms, so we have a separate room for speaking posters. We are looking for speakers, and I know many of you are grad students or have research going, so this is a very good opportunity to share your research and really hone in on your presentation skills. They're going to be 15-minute talks plus 5-minute Q&A, so like a 20-minute talk. Not too strenuous, but also not too short. You don't have to rush, but also gives to a general audience. And I hope that some of you sign up. I can see the little analytics on the rule sheets that I sent out, so I can see who's looked at it. People looked at it, but not like actually signed up. I encourage you to actually come in. And us, the data science club, we're going to be doing 3 workshops. It's more because it's an undergrad focused event. So some people are going to come in with no prior experience. So we're going to do like a data science 101, showing people like Python, Matplotlib, NumPy basics, data science 102, which is going to be like our data processing, engineering, and cleaning, and a data science 103, which is machine learning basics. And we're hoping to attract a lot of people that like, you need no prior experience. Come in and we'll teach you how to work with data and work with this data set from like a real industry source. Yeah, so now we have all the logistics together. It's all about advertising. If you're in a few of my circles, you see me just spamming messages like repeated ones. But I think that's just how advertising works. So, yeah, hope to see you there. Hope some of you. Thank you.
Yeah. And apart from that, of course, we're still looking for a new e-board. So please keep that on your radar if that interests you. Of course, this would be the QR code to show us that you're interested. So again, over time, if you guys decide that you want to become members of the e-board, because the current e-board is graduating for the most part.
Maybe everyone here is graduating. That's our problem.
Yeah. But something to think about. All right, so today we are working on reinforcement learning, as agreed. Next week will be neuroevolution, and that will be pretty interesting. And of course, after that, we'll have spring break. So it's just a quick outline for the next 3 weeks.
Yeah, neuroevolution is a good thing to end off on because we've basically done our whole like neural network sequence.
Yeah. All right. So on that note, today we're doing reinforcement learning, like we said, and this is little Jacob and Mom. He's being rewarded for good efforts and knowing his timetables. So this is a little segue into what we're doing today, reinforcement learning. So what is reinforcement learning? Well, it's like this group of different algorithms that establishes something called a policy, and you have something called a goal, and you want to maximize the return when an agent inside a certain environment is interacting with this environment. We'll go into like more vocabulary terms so that you can understand exactly what these things mean shortly. And so RL stands for reinforcement learning. Yeah, these systems can become experts at many different things. Some popular examples are like, board games. So you see like AlphaGo on the right, your right hand side, and chess. And it learns like a lot of moves that will ultimately allow it to win games as it optimizes like the rewards over the course of this game, and winning game in many cases is the reason why you play a game. And so that would be the goal. And then we'll explain some more moving forward. Okay, so what is this alleged agent that we're talking about? Well, it's an entity that actually navigates in some kind of established environment. So this agent will get some kind of reward or return that it gains from like moving through different states and positions inside this environment. And of course, we have the beautiful Kim Possible. Hopefully, I'm not dating myself. Hopefully, you guys know who that is. And James Bond 007. So what is an environment? So an environment is just basically like this world, this can't use a word to describe what it is, but an environment is like this world that you create for an agent to navigate through. In which case, if you look at, say, the left-hand side, the agent in question is a robot, and the reward is ultimately this battery. And so you see the environment is the entire, say, playing field that it's navigating between, and the agent has to essentially get to this reward or this goal, and the reward will kind of like be these points that it accumulates as it navigates to its intended destination. There's more to that, but another example of an environment would be, say, a chessboard. We have various different pieces, and the environment would be, of course, the 8x8 grid on which you play. Okay, so what is a state? So actually what we can do is a state will be, so for example, if you see on the left-hand side, we see the agent and we see this, say, turquoise environment. A state would would denote each of these individual cells inside this like entire matrix grid. And so essentially saying, if you are to make some kind of movement, you're moving from state to state, that is each individual grid, like within this matrix, such that you finally do conversion, getting into your goal. And so by textbook definition, it's basically saying like the world that contains the agent and allows the agent to observe that world state. Again, this can also be denoted through a chessboard. We have an environment, which is the 8x8 matrix grid. And then, we have multiple different agents in this context, which can be any of the various pieces of chess. So yeah, state is. So actions are the way that an agent like transitions through different states, essentially saying, hey, if I want to go from here to the door, then an action would be like me taking steps towards this door. So it's like making like actual movements. In this case, it would be me moving to the left, moving to the right, moving backwards and forward. And so agents, actions are just like the movements with which we use to navigate through different states themselves. And of course, reward. So this is something that is a pretty big deal in the context of reinforcement learning. As easily as say, maybe you guys have heard of Ivan Pavlov, a psychological experiment when a dog is being psychologically conditioned to do certain things, and you kind of incentivize good behavior with, say, a dog treat. And so what that is, that it goes to say that essentially when an agent makes successful moves or a move that would ultimately bring it closer to the goal in question, then we establish some kind of reward system where it gets like kind of like positive points, if this is described as a game, such that over time it kind of understands, okay, this is, if it's in a certain state inside this environment, when we give it reward points, it's understanding that these steps that it's taking iteratively are like actually good steps. And there's ways to calculate that, which steps are the best possible steps as we iteratively go through these environments, and we'll talk about that in a second. But again, think of it as like a positive signal to an agent, an environment that encourages whatever action that is actually taken. Okay, so now we have something called a policy, and we have a value function. So it's like, okay, we know that we have to like allegedly find good moves inside this environment, and we need to make sure that, we have some kind of way to establish, like, what does it mean that a move is like good, quote unquote. And so what we do is we use a value function, and it basically like evaluates like how quote unquote good these steps are. And again, how do we know how good it is? We use something called a policy. And basically it's like this mapping of observations to actions. So basically saying like, okay, it's a strategy that allows this agent to actually like pursue its goals. So as you'll see, like now, all of a sudden in this environment, we have different numerical values associated with each of these cells, each of these states. And so the policy will tell us, okay, like when we have different values, probabilistic values in them, like the policy is us navigating through these states and in an ideal fashion. But wait, there's more. So previously we saw, okay, we have an agent and an environment, and obviously each of the states are now determined, like they're deemed with a certain decimal point value on the left-hand side. On the right-hand side, you'll now see that there's not only one goal, but an additional one. But as well, we have this disarming black hole that will destroy everything asunder if we ever step into it. And in fact, on the left-hand side, you'll notice that the values are all, say, dark green, but on the right-hand side, now you'll see on the agent to the immediate left and the immediate bottom of it, those values are now changed. And like correspondingly, all the values around this like dark hole are now changed. That is to say that not only is there a reward for taking certain actions and hitting certain destinations, but as well there's penalty points. Say if, for example, you are a autonomous vehicle from a brand that will remain unnamed, and you unfortunately collide into something, well, there's going to be a penalty associated with that kind of thing. These are things that you don't want to incentivize your agent to do. I mean, for obvious reasons. In the context of a car, hopefully not property damage. In the context of a drone, you don't want it to collide because that would be an expensive thing to repair. And in various different contexts, you also want to make sure you're incentivizing good actions only, and you're penalizing bad actions, which in real time could become catastrophic very quickly, as you might imagine. So again, the context of the multiple goals in this and this black hole is to say, hey, you can have multiple different goals inside the environment, but as well, you can have obstacles, or in some cases, something even worse than an obstacle. Okay, So now we have something called the Q function, in which case it's like this function that predicts the kind of return that we'll get from an action in different states. So also like this is commonly referred to as the state action value function. So essentially, if you ever hear this term, maybe in an upcoming course or in any kind of like discourse surrounding reinforcement learning, you'll understand that, you know, Q function and state action value function actually like correspond, like they're synonyms, basically. So obviously, we know as people who care about machine learning, you might have the question, well, is reinforcement learning a supervised technique or is it an unsupervised technique? The answer, as you probably already know by looking at the first bullet point, is that it's neither. And moving forward, like you should understand that reinforcement learning doesn't like use labeled data sets in the same way that supervised learning would. And it's not necessarily like making sense of like patterns from disarray, like some data that's kind of like unorganized and you find like some clustering in it. So essentially what this agent is doing again is it's going through different states and trying to get an understanding of like optimal paths to navigate through to get to its ultimate goal. There's different approaches to do this, deterministic approaches, but of course, like the ultimate, like, I guess, point that you should kind of glean from this is that, again, reinforcement learning is a category that is neither supervised nor unsupervised. So this would be like a quick little example of how the agents navigating through an environment. Of course, you can see like this is yet another grid, and we have a score this time associated with this agent finally getting to what is a treasure chest in the upper right corner. And so this map, there's different map locations, of course. It's like indexed, and you can see like the indices. And so again, this agent is moving through the map in a way that will allow it to navigate to its intended goal. The reward, of course, as you might be able to see, is 100 points at this chest and 0 points elsewhere. And there are, of course, other ways to kind of incentivize like how an agent is able to navigate through an environment. In games like chess, you know, you will be able to see whether or not you'll see your reward after the game is complete. Hopefully you've won the game, but there are other like ways to adaptively like iterate adaptively improve or increment your score along the way. So that will be it for reinforcement learning as far as talking about it, theory. And we have our lovely guests from the AI Club to come and talk to us about a practical example.
So you need to stop sharing screen and use that.
Yeah.
I think you need to press escape. Make sure I mute.
Yeah.
Maybe it's there. And maximize that. Yeah, that would be a good idea.
Oh. I mean, there's definitely.
Yeah, I was just afraid that like because of the reinforcement learning stuff, like you would like die. Gotcha. Also, performance.
Okay.
Yeah. Yeah, Quinn, you also want to come up?
Science club meeting, although I do want to come more often. And I used to be on the e-board of undergrad AI club, but I'm not. But I'm really into RL, so I'm glad I'm able to present this to you guys. I'm gonna let Ben. All right, so let's walk through this notebook. So just for some background context, this algorithm is called deep deterministic policy gradient, and it's pretty similar to kind of the Q-based approaches that Tolu was just talking about. Basically, we're going to have a network learn the value of a different, and we're going to have another network that will take the output of the value learning network and use that to basically learn, given an observation, what the best action is. And the cool thing about it is, it doesn't just give you actions. Like it won't just say oh, press button 1, press button 2, press button 3, press button 4. It'll actually give you a continuous actions, which is really great for robotics control, or any time you want to get a number instead of just buttons. So yeah. So let's go through this. So first we have this Q network, which is usually what we call the network that learns the value functions. So here you can see as input, it's taken in both states, which is just the observation, and the action that it's receiving. So basically it's going to take the state, the current observation, it's going to take an action that can be performed in that state, and it's going to tell you, hey, based on what I know about the environment, when you take this action in this state, you're going to get a reward of 100 or -5 or something like that, which is basically the concept that Tolu talked about with the whole grid and learning those different penalties and rewards. So you can see it basically takes the states and actions and gives you a single value. And here we have our P network, which we're going to use to call the policy network. So again, when Tolu was talking about that policy function, this is one implementation of that. So basically this takes the state, which you can see right here, and it maps that to our action. In this case, our action is a number between -2 and 2, which is why we basically take our states and convert that to this tan H function times 2. And also for some context, just want to introduce the environment we're going to be working with. So this environment is called Pendulum. It's one of the classic reinforcement learning problems. And basically what we want to do is we want to say, given our observation of these 3 continuous numbers, which basically are the, let's see, what is it? Which is the cosine of the angle, the sine of the angle, and the angular velocity of this spinning rod right here. We want to output, what are we outputting? One number, which is the torque. And what we eventually want to do is we want to learn to take our observations, those 3 numbers we were talking about, and we want to train this to balance that whole thing right at the top. Right, yeah. So this is a super difficult task. So yeah. Yeah, and it also has to do this within a limited amount of time. So it can't basically just go back and forth forever, and eventually hit the goal. It has to basically try to speed things as much as possible, or else the environment will end and it'll be counted as a failure. So it has to learn to quickly make the pole go all the way up, and once it's up, just lock it in place. So it's kind of a complex problem. No, it does not. So basically, it has to learn to take advantage of the fact that the momentum is going back and forth, and when it's all the way up here, then it wants to move the momentum slightly upwards, and then it does no torque, and then once all the way over here, then it'll activate the maximum torque. So basically, it learns to use momentum in its calculations, and when once up here, then it learns to only use the amount of torque to make it not go downwards and upwards. How much torque you can apply? How often? Because I don't know. It actually can apply the same amount of torque, but it's only limited to -2 units of torque, or whatever it's called. So yeah, so even if you so it's right here, like even if it like applies torque like this way all the way here, like it won't have enough torque to like make it just go upwards. Yeah. Right. Yeah. So once it's up here. So. Right. Yeah. So, okay, so we set up our key network here, we set up our policy network here, and we also set up two target functions. That's actually an important thing in deep reinforcement learning. Whenever you have a neural network that learns one of these like value functions or policy functions, you also need a target network because otherwise training will get like super unstable because it'll try to like base values off of like the same like policy you're training and like it'll suck. So basically all the Q target and the Q and the P targets do is it's basically a saved version of those networks we're training. And we're only going to like kind of like periodically update them or like slightly update them every time we update our main networks. We'll see what that means in a second. So here we got our setup. Okay. So yeah, so here you can see how we're stepping through our environments. Basically, our environments, which is the environment we just talked about, at each time step gives us an observation. And we basically take that observation, move it into our two networks like we just talked about, or actually, in this case, just a policy network because it just needs to give us an action in this case. And it'll basically give us the that number, that action that it should apply, you know, the amount of torque that you give that pole. And here you can actually see something pretty interesting because when you have a deterministic policy, it might not like fully explore like the realm of possibilities to what it's doing. When we use something like this, we usually want to add some kind of noise to the either the policy probabilities or like directly to the action. So that way, like we kind of force it to like learn, oh, what would happen if you did like this completely different action instead of doing it what you wanted. And that also like helps you speed up training and like actually get a decent policy. So that's important. So let's see. So we step through our thing while we're training. Okay, so this next part is storing transitions. This is something that you have to also do with reinforcement learning. So basically, whenever you have a neural network, you basically want to also have like a data set, right? And like the bigger the data set, the better. So when you're doing reinforcement learning with these neural networks, you have to take the transitions, that is the information that you're getting from the environment. You have to store it in this giant buffer. In this case, this is a buffer of like, is it like 100,000 elements? And you basically have to take that data that you're generating by stepping through the environment and create a data set out of that. And you train those networks we talked about before on that giant 100,000 element long data set. So we've been storing the transitions. Okay. So once we store like a decent amount of transitions, we can start like actually training using our improvised data set. So basically we're going to sample a set of transitions, the information from the environment from our replay buffer. We're basically splitting it out into these tensors. And we're going to do two different training steps. Number one is probably the kind of training that you're used to if you've done like literally any other kind of work with neural networks. We're basically taking the reward that we got and we're associating that with the with our observations that we got from the environment and also the actions that we did. So you can see that our Q network, our value function, learns that given a certain action that we took and what the state was when we took that action, what the predicted reward would be. And reward calculations there are like a bit more trickier than that. You usually actually like sum up like all the rewards that you got like after you took that action because you don't want to like learn like directly like what was literally the reward like right after. You want to like learn like what was the reward you ended up getting. But yeah, you basically associate states with and actions with rewards in this case. And after you learn your Q function, you also want to take a moment to optimize your policy network as well. So basically, we're taking our value function now, and we're going to pipe another network through that. And this network just takes observations and gives the action. And we're going to then take the action generated put that into our value network, and then try to use that to like maximize the output of that other network. We're basically training the policy network directly on like maximizing the reward. And then after we do that, we just upgrade our frozen networks, our target networks. And yeah, that's actually pretty much it. So I would train this, except it takes like 5 minutes, and I don't want to just sit here for 5 minutes doing nothing. So I'll just show you like this graph of like the rewards as time goes on. And you can see like this is pretty noisy, so it does look like it's going like up and down, and usually like you want to apply speed to this. But you can definitely see that there's like kind of like an upward like trend ish as time goes on. And usually you want to do this for like 50,000 steps or something like that. So the policy does like get better as time goes on.
You just regret learning?
I'm actually not familiar with the term regret learning. Do you mean like
Penalize, you're not giving it a reward, you're penalizing. And what are you
right? Yeah. So yeah, going back to this environment, the way this environment works, I believe, is basically for the environment will end like if you manage to balance the stick on top. And so for every like time step where you're not doing that, it'll give you a reward of like -1. So you're trying to like maximize like right. Yeah, and just for debugging, I like to usually plot the losses for the value function and the losses of the policy network. And I'm more interested in the losses of the policy network because if it goes down, that means that we are like reducing our the amount that it's failing at. Yeah, so it looks like so the policy loss, unlike the value loss, is basically like literally like how good did you get, basically. Yeah, the thing about policy functions, it's kind of like tricky to like interpret exactly like what's giving you because it's not like a classical like error. It's more like like you're directly like maximizing the output of the network based on the rewards you're given. It's not like you're subtracting it like you would like MSC or something like that. But yeah, it looks like it is like. In this case, smaller, I believe. Yeah, different people plot things in different ways. Unfortunately, so not a whole lot of standardization. But now we can see how well it did. So, actually, yeah, let me do that again because I feel like I didn't show it at first. Okay, yeah, okay, so it is working. Yeah, sometimes it gets lucky. Yeah, if it gets really good, it can like
swing back.
yeah, this one. Yeah, this. Yeah, that's another thing. Sometimes it won't like see the entire state, so sometimes it'll be given like a certain like starting state that isn't like really good, so it doesn't know like what to do. Yeah, so you have to make sure. So that's part of the reason why we had that noise at the beginning. If you don't have that noise, then like it might just like learn like the same like distribution. It won't like try to do anything. So I know in RL literature we generally don't say overfit. Yeah.
States it hasn't seen it as how to do it.
Right. So that's more of like an exploration problem, which is actually a fairly tricky problem. And there's like tons of ways people have tried to go about that. Right. Yeah. All right. And yeah, I think that's pretty much it for the demo. Any questions?
Well,
Right, you're talking about this section? Right, yeah. So in the original DQM paper, which was like one of the first ways we formed DeepRL, the way we updated them was we basically like waited like every like 100 updates, we would just like replace like our target networks with our trained network, and then we would like freeze up like 100 more iterations. But this DDPG paper actually proposed something called polyak averaging, and the way that works, which I will go up here, is you basically get a number between like 1 and 0. The closer to 0 the number is, the slower the target networks will update. But you do like kind of like incrementally update them. You basically average the values of the target network with the network that we're currently training, and you like slowly like update the parameters to that. So it's like almost like a more continuous update as opposed to like every 100 updates, just replace it.
So the loss function you showed us is spiky, super spiky, it's not very smooth. So is there a way to adjust your rewards to have more incremental rewards up to the goal state so it can learn in a smooth way and just having your variable?
Right, yeah. So reward engineering is definitely like a thing. And yeah, to your point, in like way more complex environments, just like giving like a reward of like 1 if you finish, or like 0 if you don't, or like just like a -1 reward or something like that usually isn't going to work. Instead, you have to like kind of like say, oh, we'll like give you kind of like we'll kind of like give you like breadcrumb rewards, where like for like intermediate actions we'll give you like a reward of like 1. If you like collect the chest, it's like a reward of like 100, something like that.
This is more of a binary in the state where you're not being penalized, where you're so it's either did the network achieve it or did it not? So
Right, absolutely, yeah. All right. Hey.
What are you using to do this visualization package?
This pendulum thing?
Yeah.
Yeah, so that's actually an interesting question. So I'm using Gym, which was provided by OpenAI, but you shouldn't use Gym in 2023 because OpenAI no longer maintains Gym. Instead, they gave a lot of their like RL stuff that they were maintaining to this new organization called like, God, I forget what the name of it's like this whole like organization that basically took over a bunch of the stuff that Farama Foundation, there we go. But they have this like new package that's got like a slightly different interface, but basically has like the soul of like the old Gym package. So you should use that instead. Uh, like when I evaluate it like this, like am I like writing? Like am I like replaying like saved data? Yeah, this is active. Yeah, this is like happening in live time. Mhm. Right. Yeah. Yeah. So I guess the whole goal with like reinforcement learning is like eventually like you want to put this like network that you've learned like into something like concrete, right? Like a robot or like a video game character or something like that. So usually networks are fairly smaller, but they're pretty fast, and it's to the point where like it might not even like be worth it to like put this on the GPU. Usually you'll have like CPU trained or CPU ran
what kind of
networks.
are you using? It's like I almost think of this as like a classification problem. In a certain state, you need to give a certain response.
Mhm.
So are these just feed-forward networks? Are these networks?
That's also an interesting question. So these are feed-forward networks, but RNNs have definitely have like a ton of like influence in the literature. And like if you have like any kind of like continuous environment where you want to like have the agent like remember the past, then you do want to have an RNN or something like that.
Like classify the state you're in, and then give the appropriate responses.
Yeah. So two things there. First, CN.
the recurrent is the past states, right? So the past environmental state is your value, your recurrent. Let you go ahead.
So sorry, what's the question?
Would identify the state in you classifier. You classify the state you're in and then your policy network. In the state, here's the action. Right?
I think if you have
Mhm.
so for instance,
Mhm.
for also
Mhm. Yeah, that's the thing about this framework is since RL is more of like a framework than like a neural network architecture, you can take like any model and like put it through this RL framework, including language models, which is how ChatGPT was trained.
And your guest speakers for showing us our role.
Thank you.
And that concludes our meeting. So yeah, thanks everyone for showing up. And next week we have another guest speaker. So yeah, we're really being lazy here and just having other people run our meetings. But well, we're doing neuroevolution, which we had a lot of conversations about architecture search. So we're about to answer many of them. Right. Bye.